Hi everyone, welcome to online lecture 11. And today we're going to talk about multiple regression. So the reading for the next time would be in Laird, the chi-square goodness of fit, and the chi-square test of homogeneity. You will see that they are actually quite similar in nature, and we'll talk about that when we talk about the chi-square, but please go ahead and read both of those. Then for your homework after this lecture will be from chapter 12, 12.1, do both A and B, but report B only. Okay, so you're going to do both A and B and report B only. And you're going to do this. You're going to use this data as a jumping off point to complete both simple linear regression and multiple linear regression analyses. Okay, so it's like you're doing 4 things and reporting on 2. Okay. So for SLR, for simple linear regression, please check and report all assumptions. However, complete the simple linear regression whether or not you meet all assumptions, and then report as we discussed. You're going to use age as the independent variable and flu-sick as the dependent variable. Okay, so that's for your simple linear regression. So again, for that one, it's 12.1 A and B, report B only. And then for multiple linear regression, you do not need to check any assumptions. We're going to talk about the assumptions a little bit, but you do not need to check any assumptions for multiple linear regression. You'll complete the multiple linear regressions and report as we will discuss. And you're going to use flu-sick again as your dependent variable and all others as independent variables. Okay. So, and then again, you'll do both A and B, but report B only. Okay. And if you have any questions regarding that, we can, of course, talk about it more in class. This is a fun multiple linear regression example, just if you'd like to kind of dip your toes in a little bit first. And if you like TED Talks, you might enjoy this. It's called Lies, Damn Lies, and Statistics About TED Talks. And it goes through a multiple linear regression model for TED Talks and what makes some TED Talks more popular than others. Okay, so feel free to check that out. It's an optional thing, but feel free to check it out. Okay, so multiple regression analysis, which they abbreviate here with MRA. We're mainly going to focus on multiple linear regression, which is typically abbreviated MLR. Okay. So we're going to talk a little bit about the design requirements, the multiple regression model, what is R squared, how do we test R squared and the betas, or the B's, I should say, and then how do we compare models and how do we compare standardized regression coefficients. So that just gives you a little bit of an overview of where we are going. So let's start off by talking about what multiple regression analysis is. It's a method for studying the relationship between a dependent variable, so we still just have one dependent variable, and 2 or more independent variables. That's what's different. With a simple linear regression, we just looked at one independent variable. Now we're going to look at 2 or more. Purposes, prediction. Just like with simple linear regression, we might also use it for explanation or for theory building. Okay, we might want to explain a concept or a theory using this. Okay, so what are some of the design requirements? Well, you have to have one dependent variable, and that's your criterion. 2 or more independent variables, those are your predictor variables. Sample size. For sample size, you should always use a power analysis. But here is nonetheless something out there that people talk about, which is that you definitely need greater than or equal to 50 people or participants or data points. And you should have at least 10 times as many cases as independent variables. So if you had 5 independent variables, 5 times 10, 50. But even if you have 3 independent variables, you still want at least 50. And if you have 10 independent variables, you'd want at least 100. Okay. So the more independent variables you have, the more participants you tend to need. Okay. All right. So that's just a rule of thumb. So let's talk a little bit about simple versus multiple linear regression. You have one dependent variable y predicted from one independent variable x versus one dependent variable y predicted from a set of independent variables, x1, x2, x3, all the way up to xk, however many you have. In simple linear regression, you have one regression coefficient, whereas in multiple regression, you have one regression coefficient for each independent variable. In simple regression, we have r squared, which means proportion of variance in dependent variable y predicted from x. In multiple regression, we have r squared, which means proportion of variation in dependent variable y predicted by a set, by all of the independent variables x's. Okay. The general idea, multiple regression simultaneously considers the influence of multiple explanatory variables on a response variable y. Okay. So we're looking at predicting y using multiple explanatory variables. Okay, so here we have x1, x2, as I said, all the way down to xk, however many x's you have. It could just be 2, it could be 3, it could be 10, right? All predicting y. And the intent is to look at the independent effect of each variable while adjusting out the influence of potential confounders. So we'll talk more about that, but that basic idea is we might include things we're not really interested in. Let's say you're doing a study and you're not particularly interested in gender, but you are afraid it might be unduly influencing what's going on here, and it could affect your relationship between your IV of interest and your DV. You still might include it so that you can adjust for it. Okay. Regression modeling. Okay. The top is a simple linear regression model with one independent variable fitting a regression line in two-dimensional space. The bottom is a multiple regression model with two explanatory variables, two IVs, that fits a regression plane in a three-dimensional space. Now, I'm going to blow this up a little bit more so you can see what this looks like, this bottom one, okay? You're used to seeing the top one, I think. This bottom one is a little bit different. Okay. So let's look at it. Our intercept predicts where the regression line, where the regression plane, excuse me, we have a plane now, where the regression plane crosses the y-axis. Right here. The slope for variable x1 or b1 predicts the change in y per unit x1 holding x2 constant. And the slope for variable x2 or b2 predicts the change in y per unit, excuse me, the slope for variable x2, b2 predicts the change in y per unit x2 holding x1 constant. Okay, so you can see this is one slope, right? That's for x1 or b1. This is another slope, this line right here. That's for x2 or b2. We still have errors coming off of this plane. Okay. So here's our intercept. our slope for variable x1, and our slope for variable x2. All right. So let's look at an example together. We're going to look at self-concept and academic achievement in 103 people. So here's just some correlations to start off. We have general self-concept, academic self-concept, academic achievement, and grade point average. So we have some nice correlations up here, and we have some means and standard deviations down here. Okay. Now let's look at the model. Now, this Y with the little apostrophe here is the same as a Y hat. Remember we put a hat on the Y before? It says the same thing. It's your predicted Y. It's just another way to write that, okay? So what is our predicted Y in this case? Well, it's still our intercept A. That's good. Plus slope 1 times x1 plus slope 2 times x2 plus et cetera, until we get to the last slope times x. Now the b's are called partial regression coefficients. Okay, so we can think of them as slopes, but they are called partial regression coefficients. Our example, predicting academic achievement. Now we're not going to use GPA here. We're just going to use the other two, the self-concept ones. So we have our predicted Y or Y hat equals 36.83. That's our intercept. That's what I just showed you in the last picture, right? Where Y crosses the plane. Plus 3.52x for academic self-concept, plus a negative 0.44x for general self-concept. So if we wanted to get a predicted academic achievement for a person with a general self-concept of 4 and an academic self-concept of 6, we would take our predicted Y equals 36.83, our intercept, plus our slope, 3.52 times 6 for ASC, plus a negative 0.44 slope times 4 for GSC. And we would predict that their academic achievement score would be 56.23. So this is really just like what I showed you for the simple linear regression with a little more added on. Okay, so we can talk about this more in class, but this is an equation I would like you to be able to go through. And I can show you how to do it in SPSS as well. I think it's a little more painful than it is just doing it by hand. I guess it depends how many predictions you're trying to make and how many variables you have. But for our purposes, I think it's a little more painful, but I will show you how to do it in SPSS as well. But I would like you to be able to compute this kind of thing. Okay. All right. So just to help you out with that, remember we're going to do our multiplication first. Then we can go through and do our addition. Okay. All right. So let's talk about our multiple correlation coefficient R and the coefficient of multiple determination R squared. All right, that should be a full parentheses right there. R is the magnitude of the relationship between the dependent variable and the best, we'll talk about this, the best linear combination of the predictor variables. Okay. R squared equals the proportion of variation in Y accounted for by the set of, or the best set of independent variables, the X's. Okay. So When I say the best here, you might be wondering, well, wouldn't we always include all independent variables? Isn't that kind of what you asserted before, that we might include things that are not necessarily even part of our IV of interest, but just for the sake of accounting for them? The answer is yes. In an ideal world, I would go ahead and include everything. However, because of sample size, because of n, sometimes we only look for the best set or the best model containing the best independent variables. And I will share with you that there are differences of opinion here. Some people would always say, knock out the ones that are just not important. Other people would say, no, keep them in, you're adjusting for them, you're showing that you're adjusting for them. So slightly two different schools of thought here. Okay, there we go. Okay, so another picture, right? Explaining variation, how much. This big circle is all the variation in Y. We are trying to account for as much of that big circle as possible. In the inner circle is the predicted variation by the combination of the independent variables. In the outer piece here, the outer part of the donut, if you would, is the unpredicted variation. So the orange is what we're not predicting, and the inner part with the squiggles is what we are predicting. Okay. I like this one even better. Proportion of predictable and unpredictable variation. Okay, so we're going to keep with our example of academic achievement, academic self-concept, and general self-concept. So here's our academic achievement. Okay. The part of the academic achievement that we cover with either X1 ASC or X2 GSC, so with either academic self-concept, well, I should show you that. Academic self-concept, look at this, right? That's academic self-concept. GSC is right here. It's this lighter blue one. Okay, general self-concept. That's kind of the overlap. And I should show you actually the overlap of X2 and Y is only this part. Okay. So if we take the part that's for X1 and then take the part over here, these two that are for X2, that is all of the predictable explanation variation in Y. This is the remainder, which I will try to show you. If I go on the outside here, let me stop here and capture that. Whatever isn't being captured by either X1 or X2, that remainder is 1 minus R squared, and that's the unpredictable variation in Y. Now let me ask you another question. Which one do you think is covering more? So let's eliminate this part here, this blue part here that's coming from both X1 and X2. So what's uniquely covered by X1? Just this kind of white part. And what's uniquely covered by X2? Just this little part here. So which one do you think is giving us more variation, ASC or GSC? Which one is covering more variation in Y? Well, I would say it's this one. It's ASC, because this is all of this white area right here, whereas GSC is just this little area here. And then X1 and X2 combined gives us this little blue area right there. Okay. So this goes back to what I was just sharing with you. You might say X1 is probably going to give me the best fit model because X2 is only going to add this much more if I add it to it. So maybe we just look at x1. Or you might say, but x2 is adding something into it. Shouldn't we include x2, even if it's only a little bit? Or should we at least adjust for it? Okay. All right, so now let's talk a little bit about dummy variables. Let's talk a little bit about dummy variables. So multiple linear regression can handle easily if you have a continuous variable, or if you have a continuous variable for an IV, we assume that the DV is continuous for a multiple linear regression. Okay, so we're assuming the DV is continuous. If the IV is continuous, you're good to go. If the IV is dichotomous, meaning it has two categories, you're good to go. What if the IV has three categories? Then we have to use what's called dummy variables, and we have to dummy code. Okay, so smoke 2 has 3 levels, initially coded 0 for non-smoker, 1 for former smoker, and 2 for current smoker. So because there are 3 levels, we take 3 minus 1, we get 2, and that means we're going to need 2 dummy variables to code this information, and here's how it would look. Okay, so you've got your smoke 2, that's 0, 1, 2. You've got dummy variable 1, which really compares former smokers to non and current smokers. You've got dummy variable 2, which really compares current smokers to non-smokers and former smokers. And that's all you need. Now you might be wondering, well, don't you actually need that third dummy variable that compares non-smokers to former and current smokers, right? The 1 here and the 0, 0. And the answer is no. As long as you've got 2 of them, if you have 3 levels, you're okay. So I don't want you to worry too much about this. We're not going to, in this class, get too much into dummy variables. But if you have one for your dissertation, there is a piece on Layered that describes how to go through and code dummy variables. Okay, so you won't be lost there. Now let's talk about some significance tests. Okay, so let's talk about testing R-squared. Well, essentially, we test R-squared through the F-test, through the ANOVA that we're used to, right? And we can look at competing models, right? Whether we're going to include 2 variables or 3 variables or 1 variable, we can look at competing models by our difference between the R-squares through an F-test of difference of R-squares. Okay. And I'll show you how this looks in a little bit. And then testing our B's. Well, we can test each partial regression coefficient by t-tests. And we're going to compare partial regression coefficients with each other through the t-test of difference between standardized partial regression coefficients. Okay, so we'll see how all this looks. So if it doesn't make a lot of sense yet, that's okay. We're going to go through and you're going to see how it makes more sense. Okay. So let's start off by talking about testing R-squared. What proportion of variation in academic achievement can be predicted from GSC and ASC? So we found in the model that R-squared equals 0.16 or R equals 0.41 or 16% of the variance, 0.16 becomes 16% of the variance in academic achievement can be accounted for by both GSC and ASC. So if we include both GSC and ASC as independent variables in our model, our R-squared will be 0.16. We're accounting for 16%. Is that significant? We look at our F. We look at our ANOVA. F observed, what our F is in the ANOVA table, is 9.52. The critical value, had we looked it up in a chart or something, would be 3.09. That's not important because it'll just tell us in the ANOVA table the exact p-value. But we know that clearly we can reject the null hypothesis because there is a significant relationship between academic achievement and the linear composite of general self-concept and academic self-concept. Okay. Now, do we need both of those in the model? Do we need both ASC and GSC? Let's look. Model 1, here's the intercept, plus 3.38x ASC. Or if we include GSC as well, it's 36.83 plus 3.52 plus a negative 0.44x GSC. Remember these? Well, this is our slope in Model 1. These are our slopes, 3.52 and negative 0.44 in Model 2. So we're going to compute the R squared for each model. 0.160 if we just include ASC. 0.161 if we include ASC and GSC. So one thing you might ask yourself is, what's the difference between these two? It's only 0.001, which means the GSC is adding 0.1%. Yes, 0.1% of the variation here. Now we can also look at an F. And if we looked at an F and we looked at the crit value, we looked at the p-value, excuse me, if we looked at this sig value, we would conclude that GSC does not add significantly to ASC in predicting AA. So really, the academic self-concept is the important variable here. General self-concept is less important. So the thing is, general self-concept, whenever you add anything to a regression model, it's always going to account for a little more. It's always going to add something else you're accounting for. Now, if the previous literature said, general self-concept is everything, it's everything in academic achievement, and that's all there is to it, and you had found in your dissertation, aha, people didn't account for academic self-concept, I'm going to uniquely look at this. Then I would say, yeah, keep that general self-concept in your model, and you'll see that what's really important is the ASC. If you didn't put it in the model, people would argue with you and say, yeah, it's because you didn't put the GSC in the model. That would have accounted for everything. However, in another situation where you're just looking for what's most important in predicting academic achievement, you can probably just go ahead and just do this top model 1 with just ASC, because GSC isn't adding that much more. Okay. So something we can do to compare our coefficients is look at a t-test. And what a t-test is doing is it's taking our b minus our beta, our standardized, over the standard error of b, with n, our total n, in this case I think it was 103, minus k, minus the number of predictors, minus 1. Okay. So we have negative 0.44 minus 0 over 14.24. We get a negative 0.03, and we're comparing that to 1.97. This, now you will never have to do this equation. I'm just showing it to you, okay? I will show you how it looks in SPSS, and that's what I'd like you to be able to understand, but you don't have to worry about this equation, okay? So, but basically what it's saying though is that the GSC is not significantly different from 0, and it's not really contributing to the model. Okay. So in comparing partial regression coefficients, what's the strongest predictor? And we're comparing the B's for GSC and for B's for ASC. So one way to do that is to not just look at your B's, but look at your betas. Look at these, the funny B, okay? Look at your standardized partial regression coefficients or your beta weights or your B's. And these two are much more comparable. So these are on the same scale. This is 0.417. This is negative 0.038. Now, I don't take issue with the negative or positive. That doesn't matter at all. But 0.417, if you just took the absolute value, you took away the negative sign, right? 0.417 is a lot stronger than 0.038. It's a lot larger number. It's further away from 0. So ASC is stronger predictor than GSC. Okay. So you can just look at your beta weights. You can look at the t-tests, and it'll all give you the same information. It'll all tell you what's important in the model and what may not be. Okay. Now, I just want to share with you a little bit about different ways of building regression models. They're simultaneous while all the independent variables are entered together. And that's kind of what we've been talking about, and we'll probably continue to talk about. Now, stepwise is when independent variables are either entered or removed from the model according to some order. It could be by the size or correlation with the dependent variable or the order of significance. So in other words, you could do a stepwise, you can do one that's forwards, and we'll just enter them until we get to non-significant ones. Or you could do backwards, where we start with everything in, and then we take them out as they're not significant. That's another way to go. And finally, there's hierarchical, which is when independent variables are entered in stages. This is really for when you have either interactions or a whole bunch of independent variables, and maybe first you enter in things that you aren't interested in, but you're afraid may account for some of the variance, and you need to kind of put them in the model to adjust for them. So maybe you'd put in gender, race, socioeconomic status, those sort of things. Then maybe as a next step, and you'd put them in all at once, then maybe as a next step, you'd introduce your independent variable or variables of interest. Okay. Let's talk about the assumptions real quick. Now, remember, I'm not going to have you run assumptions, but I would like you to be familiar with the basics of what they are. Okay, so you have to have one dependent variable that's measured at the continuous level, either interval or ratio. If you have an ordinal one, there's a different regression for you, but not this one. Assumption 2, you have 2 or more independent variables that are measured either at the continuous level, interval or ratio, or nominal, which it means categorical, right? And if it's dichotomous, you're great. If it's more than dichotomous, if you have more than 2 categories, you've got to create those dummy codes, those dummy variables. Okay, now we get into the non-design assumptions. You should have independence of observations, which you look at through the Durbin-Watson statistic. There needs to be a linear relationship between the dependent variable and each of your independent variables, as well as the dependent variable and the independent variables collectively. Your data needs to show homoscedasticity of residuals or equal error variances. Okay. We talked about that for simple linear regression. And number 6 is new. Your data must not show multiclinearity, which basically means our IVs can't be too highly correlated with each other. What's too highly correlated? You look at the test for multiclinearity to let you know. Typically, you're okay with 0.6, 0.5. That's where you kind of want to live. If you're up by the 0.9s, you're typically not okay. Okay, assumption 7, there should be no significant outliers, high leverage points, or highly influential points. We kind of talked about this a little bit with regression, how there can be outliers and some of them can be more influential than others, like we talked about with McDonald's, Ford, and Pepsi. And McDonald's was really influential. Okay. And finally, assumption number 8, you need to check that the residuals or errors are approximately normally distributed. Okay. Let's go to Laird and talk through an example. Now, we're not going to talk through the actual assumptions because I said we're not going to get into those, but we are going to talk through the rest of it. We're going to talk through how you actually run one. So just give me a second to get to Laird. And we'll start with the example and data setup, and then we'll see if I have to sign in again. Okay. Let me just make sure that I am sharing. Oh, no. Sorry, guys. I just wanted to make sure I was sharing what I thought I was sharing, and then I accidentally stopped the share. Okay. So a health researcher wants to be able to predict maximal aerobic capacity, or VO2 max is what I'm going to call it, which is an indicator of fitness and health. Now, normally to perform this procedure, it requires expensive laboratory equipment and necessitates that an individual exercise to their maximum capacity until they can no longer continue to exercise due to physical exhaustion. Now, this can put off those individuals who are not very active or fit, and those individuals that might be at higher risk of ill health. For these reasons, it's been desirable to find a way of predicting an individual's VO2 max based on more easily and cheaply measured attributes. To this end, the researcher recruits 100 participants to perform a maximum VO2 max test, but also records their age, weight, heart rate, and gender. Heart rate is the average of the last 5 minutes of a 20-minute, much easier, lower workload cycling test. Now, the researcher's goal is to be able to predict VO2 max based on age, weight, heart rate, and gender. Okay. So I'm just going to point out, this is kind of important, that VO2 max, age, weight, and heart rate are all scale variables. They're all continuous. And I would even go so far as to, well, I will go so far as to say they're all interval or ratio. Gender only has 2 categories here, male and female. So that's easy because it's dichotomous. Had it had 3 categories, 4 or 5, however many you like, we would be creating dummy variables here. Had it had 3 categories, we'd create 2 dummy variables, 4 categories, 3 dummy variables, and so on. And then we have a case number, which is just an identification number, which we'll call nominal. Okay. Here's the variable view in SPSS statistics. One thing that they point out, and I'm just going to have you go ahead and follow what they like here, is under role, we almost always have input, and they're saying change that to none. So I will say you should go ahead and do that as well. Always change role to none. One other important piece. Notice how we have entered female and male or dichotomous variable as 0 and 1. That's what you want to do. Use 0s and 1s whenever you have categorical variables. Okay, so you can make male 0 and female 1. You can do it the other way. It doesn't matter, but you've got to do 0, 1. Okay, otherwise it's going to foul you up in the long run. Okay. All right. right, and here's our data view. They must have their toe tag on. That's how we're able to see male, female, as opposed to the 0, 1 that they entered. Okay. Let's look at how we would conduct the procedure. Now, I am going to have you conduct the full procedure here. We'll check off everything we have to check off, but then we're going to ignore a lot of the output, and we're only going to focus on the interpretation. Like I said, we're not going to do the assumptions. Okay. So you go under regression linear, just like you did for simple linear regression. Under dependent, you put the VO2 max, that's your Y, that's your dependent variable. And under the independent variables, you're going to put age, weight, heart rate, and gender. Notice that you're putting your continuous and dichotomous, or I should say categorical variables, in the same spot here. Again, had you created dummy variables, we wouldn't put gender over here. We'd put in our dummy variables that we created instead. Okay. Then under statistics, we have a lot to check off. Estimates, confidence intervals, model fit, descriptives, part and partial correlations, collinearity diagnostics, Durbin-Watson, case-wise diagnostics with outliers for 3 standard deviations. It's funny, the one thing they didn't check off here, I think is interesting, which is the R-squared change. But that really only makes sense if you're not putting everything in at once, really. So I think it's an interesting piece. If you want to include it, you can. It's not going to hurt anything. Okay. So click on the continue button, and then you'll click on the plots button, and then you're going to check off histogram, normal probability plot, and produce all partial plots. So here, here, and here. Just check those off. Click on the continue button, go to save. And you're going to save unstandardized, studentized, deleted, cooks, and leverage, and include the covariance matrix. Okay. I can tell you that, well, the cooks, the leverage, the studentized, deleted, we're not going to use any of that stuff. Okay. Click the continue button and click OK. I am having you just run everything just to give you a little bit of experience in checking off all the things. But like I promised, we are now going to skip ahead to page 15, where we interpret our results. So what's going to be our process of interpreting results? Well, first you need to determine whether the multiple regression model is a good fit for the data. Okay, and we're going to look at that shortly. Second, you need to understand the coefficients of the regression model. Well, we talked about that too, right? So first thing, we're going to look at the model summary, the ANOVA tables, all that kind of good stuff. And then we're going to understand the coefficients. We're going to see what is significantly or not significantly contributing to the model and how much. And then we can make predictions of the dependent variable based on the values of the independent variable. Now, this is where I promised I would show you how you can do this using SPSS. We'll also look at it one more time by hand. Okay. So understanding the model. Okay. So this is just telling us everything that went into the model: gender, age, heart rate, and weight. And they all went in at once. Okay. Next, determining how well the model fits. Here we have our R, which looks very nice and healthy, and our R squared and our adjusted R squared. Okay. So remember, 1 would mean perfect association. We're at 0.76, which is pretty strong level of association. Okay. Now let's look at R squared and adjusted R squared. R squared 0.577, which would mean 57.7% of the variance accounted for. However, this is just for the sample, not for the population. So there's something that we do called an adjusted R squared, which is supposed to be for the population, and it adjusts downward a little bit. This is considered to be positively biased or inflated, right? So this just adjusts it down a little bit. So now we're down to 55.9% of the variance accounted for. Now, I would say that while you don't really always have to report R, well, you should probably report R square and adjusted R square. We'll talk more about reporting in a little bit. Then we come down to the ANOVA. So far it's looking good, right? It's looking good. We come down to the ANOVA. Here's our sig value, P less than 0.001. They're not using APA here, so they're saying P less than 0.0005, but we're going to use APA and say P less than 0.001. And just to show you how you would report this, F parentheses 4 comma 95 equals the F value 32.393, P less than 0.001. Okay. Now let's go ahead and interpret our coefficients. So we're going to go to this box with coefficients. Now, the top box, the top line, I should say, is our constant, is our intercept, and we don't care very much about that. We still need to put it into our equation, and I'm going to show you that, but we don't really care if it's significant or not. It's not that interesting. So here's our regression equation. We have predicted our VO2 max, that's what we're trying to predict, right, equals constant 87.830 plus negative 0.165 times age plus negative 0.385 times weight plus negative 0.118 times heart rate plus 13.28, plus 13.208 times gender. And gender, remember, is either 0 or 1. So if it's 0, anything times 0 is 0, right? That'll just go away. If it's 1, it'll stay at 13.208. Okay. So again, we show that our constant is significant. Woohoo, we don't care. Now we're going to look at our independent variables. Age, significant, 0.010, less than 0.05. We can also look at our confidence interval here and note that it doesn't cross 0. 0 is what we don't want it to cross. This and this should line up. In other words, if you get a significant value here, this 95% confidence interval should not cross 0. If you don't get a significant value here, this should likely cross 0. It's not 100%, but it's pretty likely. Okay. So that's age, and there's our confidence interval that we just talked about. And then we can look at the rest. We can look at weight, P less than 0.001. Heart rate, P less than 0.001, and gender, P less than 0.001. So we have a unique situation where all are significant. Now, if you're curious how important they are, we could look at these standardized coefficients, these betas, to kind of compare. And we can see that gender and weight seem to be really important. And so is heart rate and age, but maybe a little less so. Now, it's kind of tough too, because Gender only has one change from 0 to 1, whereas all these others have multiple changes, right? The age goes from 20 to 21 to 22 to 51 to 52 to 71 to 72, etc. Okay. So here's our gender variable. So before we go to the gender variable, let me just make sure this makes sense. So what we're saying is for every increase in age, our VO2 max goes down, negative, goes down by 0.165 points. For every increase, the weight was measured in kilograms, by the way. So for every increase in kilogram, our VO2 max goes down negative by 3.385. And for every increase in heart rate in beats per minute, our VO2 max goes down by negative 0.118. So if you were interested, let's say you wanted to not consider every year, but you wanted to consider every 10 years, then that would mean it would go down by, for every 10 years, our VO2 max would go down by 1.65. I just multiplied by 10. Okay. So now let's talk about gender a little bit. Our dichotomous gender variable. And this has a slightly different interpretation than continuous independent variables. So the way I think of it is that as you go, and let me get this part right, which one was the one with 0? Well, female 0, females were coded as 0. So as you go from female to male, we get an increase in VO2 by 13.208. Or said another way, males are predicted to have a VO2 max of 13.208 higher than females. Okay. So here again is our equation. (87.83) minus 0.165x times, negative 0.165 times age, negative 0.385 times weight, negative 0.118 times heart rate, plus 13.208 times gender. Now, if you like pluses instead, you could do plus the negative 0.165 times age, plus the negative 0.385 times weight, plus the negative 0.118 times heart rate. Would do the same thing for you. Okay. Now, this is actually really interesting. I won't go into too much detail about it, but it could be helpful for those of you considering a multiple regression for your dissertation. It's like, it's about how you might build models, and we've talked about it already a little bit so far, but it basically is talking about, do you want to use data to help you decide what's really important or what's really not important for including in your model? Do you want to use theory-based considerations? Do you want to use both? So I would take a look through that and certainly let me know if you have any questions about it, but we've kind of talked about it a little bit so far. Now, predicting the dependent variable. Let's talk about this. Okay, so we've got our predicted variable and we can sub in, let's say we were interested in a male who, so let's start at the beginning. We'll first put in the 87.83, right? That's always the same. Minus 0.165 times 30 years old, minus 0.385 times 80 kilograms, minus 0.118 times 133 beats per minute, plus 13.208 times male, because 1 is male, equals 49.59 milliliters per, not good at this, 49.59 VO2 max. Okay. So that's how that looks. And then you would just go through, do your multiplications first, then do your addition and subtraction. And that's what you would get. So feel free to practice with this one if you'd like. Okay. How do you do it with SPSS? What I've been promising to tell you. Okay, go to, this is very similar to how you did it for simple linear regression with SPSS. Go to general linear model, go to univariate. Put your dependent variable by dependent variable, VO2 max. Put your independent variables by covariates, age, weight, heart rate, gender. Then click paste. It pastes it into your syntax window. Then we're going to add the following line. Just before design, okay, we're going to add this line called /L matrix equals all 130, 80, 133, 1. So let's go through this. All plus 1 for the intercept, plus 30 years of age, plus 80 kilograms, plus 133 beats per minute, plus 1 for gender for male. Okay. And it will give you what you want. And this is just showing you, you have to do it in the same order as what it appears in the design. So 30 years of age, 30 goes with age, 80 goes with weight, 133 goes with heart rate, 1 goes with gender. And the 1 is always first that you enter because that's for your intercept. Okay. Then you would click run all. And then here would be your result. Okay. Our contrast estimate, 49.628, with a confidence interval of 47.962 to 51.294. So I know I'm kind of biased toward probably doing it more by hand, just because I think it's a little bit easier. But I guess the nice part about doing an SPSS is you get that confidence interval too. Okay. Reporting. So I don't want you to include all the assumptions in your reporting, but let's talk through what I would like you to include. So let's start with this. A multiple regression was run to predict VO2 max from gender, age, weight, and heart rate. The multiple regression model statistically significantly predicted VO2 max. Here's our F, remember from before. Now they only report the R squared here. I would like you to report the adjusted R squared too, and I'll tell you why in a second. Okay. All 4 variables added statistically significantly to the prediction, p less than 0.05. Regression coefficients and standard errors can be found in table 1. Here's table 1. Okay. Now, here's why I told you to include R squared and adjusted R squared, which by the way is delta R squared or change in R squared. Okay. Actually, it really should have been adjusted as opposed to change. Okay, we won't worry about that. Just report R squared and adjusted R squared so you don't have to go through this. Then, I mean, again, if this is your dissertation, you're going to have to make a table like this, but this is just for class. So I'd say just copy this from the output. Okay, so if you remember, let's see if I can find it again. Here we go. This output table right here, this guy, has everything that you need to show. Okay, so I would just copy this over to your results. Now, if that's not an easy task, we can talk about it, but there are things called like snip and sketch, which every Windows computer has. I think Macs are even better at capturing things like this. So we can talk through how to capture this, but and if it's a huge deal, we'll talk about it, but I think it should be not too bad. Okay. Now there's one other thing I would like you to do, and it's at the bottom of this. Okay, let me put it on APA, excuse me. Predictions were made to determine mean VO2 max for male individuals who were 30 years old, weighed 80 kilograms, with a test heart rate of 133 beats per minute. The mean VO2 max was predicted to be this, with a 95% CI of this. So I would like you to predict one thing for your homework, for the multiple regression. So you can choose whatever you like. Can't choose all zeros, but aside from that, you can choose whatever you like for each of those variables. You can do it by hand, or you can do it using the SPSS, okay, as I just showed you. If you do it by hand, you don't have to report the CI. If you do it using SPSS, please go ahead and report the CI. And I just want you to try it for one of the multiple regression, okay? So that would, and it would only be for the one you're reporting, right? So don't do it for the one you're not reporting. So it would just be 12B, okay? So that is the other piece I'd like you to do. So a relatively short write-up, right? You're just gonna go ahead and write this little piece right here, copy and paste the table. And if you can't do that, maybe highlight the table in SPSS or do something just to show me you know which table it is. And then go ahead and do one prediction. Okay, all right. And that is all I have for you guys. So I will give you a heads up, chi-square. All we're doing that remains is chi-square, and then just a very brief discussion of some other types of regression that exist, kind of like we did with the ANOVAs when I gave you a couple of slides about other ANOVAs that exist. We'll do the same thing here for other regressions, but then that'll be it. So in the meantime, stay well, and I'll talk to you soon.